el webinar y también descargar la presentación. De acuerdo. Vale, entonces bienvenidos. El webinar de hoy vamos a abordar temas relacionados con la seguridad, con la ventilación, la detección de gases en sistemas de baterías para almacenamiento y respaldo, repasando normativas, tecnologías disponibles y mejores prácticas para garantizar la seguridad. Nos acompañará Jeff Donato, director de productos de seguridad en H2Scan. Él tiene más de 30 años de experiencia en la industria de baterías y es miembro del IEE Power and Energy Society, experto en soluciones de seguridad para aplicaciones de almacenamiento energético. La presentación, como ya sabéis, será en inglés. Y con esto ya puedo dar paso a Jeff para que empiece la presentación. Jeff, can you mute your microphone?
Okay, thank you.
Okay.
All right, thank you very much for joining me today for this webinar on safety when it comes to hydrogen in battery rooms. And today, I'm going to focus on the hydrogen topic. I have a much broader presentation on all safety topics within Europe for battery rooms. And I'm also presenting the same topic at the NIBS conference coming up near Telford this coming November. So that's, if anybody's going to be there, you'll hear this same topic again at that symposium. Just a little bit about myself. Advance my slide. I've been at H2Scan for about 3 years, but I've been in the battery industry for over 30 years. And I started out in the motive power market with forklift batteries. I spent probably 5 years in that market and then moved to the utility and telecommunications markets. And then I spent 10 years with Emerson Network Power, which is now Vertiv. And then I went another 10 years in the safety industry, working with various companies to enhance their safety in battery rooms when it comes to seismic protection, as well as anything related to safety in the battery room. I'm current chair of one of the IEEE working groups and very active in the standards committees. And I recently became active in just teaching about European standards when it comes to IEC standards and other regulations within Europe. I'm just going to jump into the to why we're talking about this. And there's been obviously over the years several battery incidents that could be related to hydrogen. Some of them are related to other safety issues, but it's created an enhanced awareness in the marketplace when it comes to hydrogen systems. And I think that over the years with the different development of different battery technologies, especially in energy storage, there's been a lot of pressure with the fire officials and also building officials on how we handle anything flammable inside of a battery room. And that may be something related to how batteries are evacuating hydrogen, how we detect hydrogen, and what our mitigation plans will be. This is a very popular incident that happened in California, and this is a good example of what caused the industry to create more regulations. And like I said, the other incidents that I put on the prior slide shows that this is not pertaining to one particular country. This is global. And so in this particular case, this was a battery system that was normally operating, and it was on float charge, and they had a problem with the gas purge system inside of the room. and the room accumulated hydrogen and created a 37 square meter hole in the ceiling after a few days of buildup of this hydrogen gas. So uh, we do have a risk, and some of the risk is not just because of the batteries emit hydrogen. Some of the risk is how our facilities are constructed, how we actually have our detection systems put together, and also what is our mitigation plan if something were to go wrong with any system, and that includes a mechanical failure. Like in this case, this was not a problem with the battery. The room was constructed properly, but inadvertently a maintenance person or a facilities person decided to turn off the ventilation system, and so therefore created an accumulation of hydrogen. So things that we have to consider when dealing with hydrogen, um, we have to consider best practice standards in the marketplace, which of course in this case is your IEC standards. We will go over a little bit about what those say. We also have any kind of local regulations. And one thing I like about European regulations is that this final decision is typically made at the local level. And so you may have these best practice standards and governing laws for each country, but most of the time, the local authority will have the final say about how these safety systems are dealt with. And so staying informed about best practices, about regulations, and is very important because they changed often. I know, and a lot of times our standards, we change these standards every, it could be every 10 years in some cases, and other standards change every 3 years. So keeping up on the latest regulations is important to make sure that we're equipping our facilities with the correct uh, devices, and also the correct methods of evacuating hydrogen and dealing with even new technologies coming out. We're very used to dealing with lead acid batteries, and of course we'll talk about lithium batteries and how that plays into these regulations. But we also have new emerging technologies coming out, as we all know. I've been doing some work on cabinet best practices and what we put inside of cabinets. And of course, we have to deal with all of the different technologies when it comes to not only lead acid and lithium ion, but also sodium ion and zinc air and a lot of the other emerging technologies coming up. And so when we look at the European standards, and we can see, of course, there are a lot of different things that we have to consider, and many of you work within these standards committees, and are very familiar with these safety regulations. Of course, I'm going to focus on, of course, the safety in the room, and that, of course, is any kind of safety requirements like the IEC 60086 or 62485. And so these standards are, of course, not just with construction of batteries, but how we actually install them and how we deal with them on site. I will bring your attention to this particular standard that has come out in the global market, and this is NFPA 855. At IEEE, we have taken an active role with this standard. The first publication with NFPA 855 that came out was actually created without a specification. It was almost created in panic, and the reason why it was created is the fire marshals or fire chiefs were putting a lot of pressure on the National Fire Protection Association to develop a standard that includes all the energy storage batteries in the market. And they created this document, which has gone through a couple of revisions. And this revision, this 2023 revision is the most current and includes all battery applications, including standby power and energy storage. And because of it, we're seeing adoption all over the world. And so in this case, what we're seeing is not only is this used primarily in the U.S., but it's also used in many other countries. And the requests that we see for help with as it relates to safety systems have related back to this document in many different countries. So I think it's taking a very much a global presence. So the premise that I'm just going to, or the items I'm just going to cover within this standard that also relate back to IEC, but there's a few differences within the two documents. The first thing we'll notice is that in this document, they always recommend hydrogen needs to be kept below 1% of room volume. The IEC basically says that it needs to be kept below 4%. Also, note that there needs to be a 2-hour backup on any safety system. So this means any kind of gas purge system, any sort of battery monitoring system that may be monitoring lithium batteries, or any sort of functional safety system. And then finally, we'll talk about this a little bit more in this presentation, that we also have to have a hazardous mitigation plan. And what this basically means for hydrogen is that we cannot have alarms that just are audible alarms in the room anymore. We have to have the alarms go to some sort of monitoring point, whether that be a fire panel, a building management system, some sort of a system that notifies somebody to be able to take action. And so just like the photo we saw in the prior slide, where we had this explosion in the ceiling, the reason why this explosion happened was that the alarm was audible, but it wasn't transmitting to somebody to be able to take action. The fire department actually showed up to evaluate this site when alarms were going off, and they didn't see any alarms in the fire panel. So they left the site, and they assumed that it was something else in the building creating the noise. So in this case, it was a missed opportunity to mitigate this hazard. So some of the abnormal conditions I'll bring to your attention that we need to consider. It's not just normal operation that we have to take into account when designing these systems. So one thing that's been that I've seen a lot more enforcement around is ventilation system failure. So a lot of times the hydrogen mitigation or detection systems, whether that be just a constant running fan, or something even more advanced, like maybe a fan on a timer, is that they didn't really allow for the mechanical failure of that system. So what happens if the fan fails? And that's something that a lot of authorities are asking questions about today. So they want to know, what is the mitigation plan if we have a mechanical failure? And then also, is the mitigation system or the gas purge system moving enough air for other types of events, best case and worst case scenarios? And I'm going to show you an example here in another slide. It's about 3 or 4 more slides ahead, that shows you what an example of the air exchange that's required for these various types of conditions. So we have seen where batteries are accidentally left on equalized charge. So can the gas purge system handle that sort of, or the ventilation of the room handle that sort of condition? Also, thermal runaway, if there's a condition that maybe leads to that, which leads to gassing. I'm going to give you an example I don't have a slide on it, but I'm going to tell you verbally about a situation that happened with valve-regulated lead-acid batteries with thermal runaway. And then, of course, charger runaway being, it's a very rare condition, of course, where the charger ramps up to maximum charge voltage. And so we're required to have a mitigation plan for each one of these conditions. The one condition I was talking about where I personally went to a site that had a valve regulated battery and thermal runaway. It was at a defense contractor, and they had a room full of GNB or Exide Absolite batteries, and they were the 20-year design life valve regulated lead acid batteries. And there was it was in a very small room, and the room was filled with about 4 strings of large batteries. So the room was a good size, but it was small for the amount of batteries they had in the room. And above the room was a lady's. I'm not sure which term you're going to use in Spain, but a lady's bathroom or a restroom, and over a long weekend, the batteries somehow went into thermal runaway. The temperature rose so high that it took all the water out of the toilets above in the room above it, and they did not have any thermal runaway protection other than what was in the UPS. And so, if they were to have say a battery monitoring system or even a hydrogen detection system, I'm sure they would have received an alarm that the batteries were in high temperature and also the batteries were gassing, because of course the valve regulated batteries will gas once the cell reaches a certain pressure. The valves will open and emit hydrogen. So in that case, they were very concerned about hydrogen accumulation in the room, and they installed the proper detection systems. They installed a cell-to-cell battery monitoring system, and they also installed hydrogen detection, and then they put temperature sensing in the site. So there was a lot of mitigation plans that went into the room after these events occurred. And so we have to keep an eye on concentrations. I also had a site in New York City. It was a valve regulated site. They were the typical 12-volt valve regulated batteries, and they had 3 rows of batteries in 3 aisles, basically in this UPS data center room. And the outside aisles were cool, but the inside aisle was very warm. And there was a hydrogen detector above the middle aisle, and the customer said the hydrogen sensor kept going off because of basically hydrogen accumulating on the ceiling, and it was due to the temperature they were operating at. So they had the charging of the battery set for 70 or 25 degrees C, but they were running the room at a much higher temperature in the middle of the aisle, so causing the batteries to gas. So there's a lot of times we have to look at monitoring, maybe not only a single point in the room, but if the room is large, we also have to monitor multiple points for temperature and maybe also for hydrogen as well. So making sure that we handle those best and worst case scenarios and have properly designed systems, properly designed airflow in the room, and of course having trained personnel. And that's one thing that I've noticed is that personnel are great when it comes to scheduling contractors, but a lot of facility managers are not necessarily trained in how to deal with hazards such as spills and hydrogen hazards. And those sort of mitigation plans. So we definitely in the whole industry can do a better job at increasing our training when it comes to end users. And then of course, like I said before, making sure we have an alarm going somewhere. It's not just an audible alarm in a room. It has to have an enunciation that goes to a system that will activate an action plan. So hydrogen, when we talk about hydrogen and where we see the alarm threshold set, and also what the overall properties of hydrogen is, that the hydrogen is explosive at 4%, and that is what we call the lower explosive limit. The upper explosive limit, which is basically where it stops being explosive, is 75.6%. So there's a vast range of a vast range where this is explosive, and so because of this vast range, we typically set alarm thresholds way down here in the 1% and 2% range. So most of the hydrogen sensors that you see have a cautionary alarm at 1% and then a critical alarm at 2%. So the goal is that we don't want to get anywhere near this 4% range. And like I said before, the IEC basically says that we have to keep below 4%, but a lot of documentation doesn't necessarily say where we should set our alarm thresholds. So the NFPA 855 came out with, we really need to set it at 1%, so we have enough time to deal with any kind of mitigation strategy before it gets to the explosive level. This is an example of a real data center room. It was I'll tell you, it was a ticketing center for a very large theme park, and this is in South Carolina. They had 2 strings of 23 plate batteries, 240 cells, lead calcium batteries. The room size was only 15 meters by 12 meters. It was obviously they had to go very tall on the battery racks just because it was such a small room. It was 3 tiers of vented lead acid batteries, and so they asked for an evaluation of how much air exchange they need to maintain below 1%, because the room was so small and they had quite a number of batteries inside the room. And so we used a guide that has been out for several years. It's the IEEE ASHRAE guide for ventilation of thermal management of batteries for stationary applications. The nice thing about this document is that it takes into account the actual battery type, almost all the way down to the model number. They have a calculator that if you put the room size and the model number of the battery into their calculator, they will give you the air exchange needed to maintain the 1%. And so in this case, they needed the 5.4 square meters per hour to maintain just their float charge. Now, if they were to go to boost, equalize, or finish charge, then the number jumps up to 18. And so if you're just sizing for this particular room, you have to take into consideration this best and worst case scenario. Now, charger runaway obviously is very dramatic. It's a very rare condition. And this is basically where hydrogen detection were to come into play, because nobody's going to size a room with this kind of ventilation. So you would rely on your detection to see if there was any sort of a anomaly like that that's going on. And as we know, most of the time, if you have any kind of event like this that creates that much hydrogen and it's a lead acid battery, pretty much shutting off the charger will remedy the condition. And so it'll stop the hydrogen from being produced and evacuate the room. And this is where we find a lot of facilities are connecting their hydrogen sensor to a relay that will turn on or off a fan. And that's a very good idea, just because it's something that happens automatically, and it's very easy to set up with the correct equipment. And also, so when you get a notification that the the ventilation system turned on at 1% hydrogen. And then you can simply monitor to make sure that the hydrogen is being evacuated properly. And it's a monitoring situation and not necessarily having to take a lot of action. Now, the interesting thing about hydrogen accumulation in a battery room is that it happens very slowly. And in this case, what we learned in this room is that if they were to turn off their ventilation systems and there was absolutely no way for hydrogen to escape, if the room was sealed, it would take 6 days for hydrogen to accumulate. So if we remember back at the picture of the ceiling being damaged because of hydrogen accumulation and an ignition of that hydrogen, even though the alarm system was going on for 3 days, obviously the condition was going on for much longer. And because rooms aren't completely sealed, they probably had this condition, they probably had that ventilation system off for a month or more. And so I would say well over 30 days. And then time to accumulate to 4% without ventilation is 23 days. So you don't need a very fast sensor. I would say that most of the sensors out there today meet the specifications for making sure you mitigate under normal circumstances. And then of course, boost, equalize, charge, it's 41 hours in their particular case for 1%, and then 164 hours to reach 4%. So very, very slow buildup of hydrogen. So there's a lot of time to activate your mitigation plan if something were to happen. So let's talk about how we say the elephant in the room, lithium batteries. So lithium batteries, of course, are not normally gassing. We know they only gas under thermal runaway conditions. But this is a UL 9540A test report that I pulled for this particular battery type. And as you can see, hydrogen is one of the most prominent gases that actually come out of a lithium battery. Now, of course, we're not going to measure nitrogen because obviously it's an inert gas. We also have concentrations of carbon, carbon dioxide that come out. And again, we're probably not measuring that. So hydrogen seems to be the gas that we want to measure to detect if the battery is gassing. Now, the standards are written just like the lead acid battery to say that we have to protect against accumulation. But what we are seeing in the industry is that manufacturers are using hydrogen detection for early detection, along with their BMS, their battery management system or emergency management system, however it's stated depending on which manufacturer it is. But in any case, if you're using a sensor for early detection in a lithium battery, it's going to have to be very fast. And so it's going to have to be in the seconds of detection. And so in this case, 30 to 40% of it is hydrogen. And obviously, once we start gassing these batteries, things go bad very quickly, right? So, all kinds of mitigation strategies that are already built into these containers. Obviously, they're monitoring heat, monitoring smoke, monitoring for fire, also monitoring gas and activating deflagration vents and all kinds of safety systems that go on with lithium batteries. But obviously, we typically find that hydrogen sensing is put in at the manufacturer level for energy storage. But we're finding in the data centers and UPS, a lot of times the hydrogen systems aren't installed at all. So that's something that we're hoping to take a correction on in the industry to say more safety is better, the more secondary detection systems you have in place for lithium batteries is better. Obviously, when dealing with UPS systems, we also deal more with personal safety than we do with just asset protection. Another application that we find a lot of sensing in would be forklifts. I mentioned I came from that industry, so it's an industry that has always just relied on its building exhaust fans, but now we're seeing the authorities are wanting some sort of sensing put in. and audible alarms that alert the operators that hydrogen has been accumulating. And so they're putting this as a part of their emergency plans. And again, if there isn't redundancy in ventilation, then a lot of authorities are asking for detection as the secondary, as basically the redundancy in the system. And then, of course, even though this isn't a battery, we're seeing a lot more fuel cell powered forklifts. And so we're seeing a lot more exactly the same application as batteries, except you're measuring hydrogen that might be coming out of the fuel cells or the fueling stations. One thing I will mention in both scenarios, and even in stationary battery applications, is that most hydrogen sensors have a cross sensitivity to CO or carbon monoxide, and most all carbon monoxide detectors are cross sensitive to hydrogen. And so if you have anything that produces hydrogen in an area, whether it be a battery system, a fuel cell, anything like this, and you're also having to measure for carbon monoxide, you're going to want to measure for both hydrogen and carbon monoxide so you can distinguish which is hydrogen and which is CO. So for example, we had a auto manufacturer who was measuring for carbon monoxide. Their carbon monoxide alarms kept going off, but they were using forklifts with hydrogen fueling stations. And what they were measuring in their carbon monoxide sensors was not carbon monoxide, it was hydrogen, and it was confirmed that way. So be aware that a lot of technologies, when we go through the sensors here in a moment, you're going to notice that a lot of sensors have cross sensitivities. And so that's something that has to be taken into account based on the system. So these are common hydrogen detectors that are in the marketplace. This is what we see in battery rooms mostly. We see TCDs, or thermal conductivity detectors, catalytic bead sensors, metal oxide sensors, and solid state precious metal sensors. And you can see the date that they were all created. So the oldest, of course, is the TCD, created around 1913. And this basically measures the gas mixture by assessing the thermal conductivity. And then of course, varying gases have different conductivities, and it's weighted against the average. So this is a very fast sensor. It's been around a long time, but it also has a lot of cross sensitivities as well. And that's something that you'll have to consider if that's right for your site or not. There's a very common one that's in vented battery rooms, is the catalytic bead sensor, and a lot of you are probably most familiar with this. This device has been around since 1927, and it uses basically catalytic beads, and when there's a carbon layer that is over the bead, and when hydrogen or any kind of gas interacts with that catalyst, that carbon layer, then it actually heats up and causes a resistance change. And that and you'll notice that most of your catalytic bead sensors, I'll just make a side note, that most of your catalytic bead sensors are encapsulated in an explosion-proof case. And the reason being is that because when the catalytic beads are met with gas and they do heat up, sometimes they can heat up so much it actually smolders or causes a flame inside. And so it's what happens inside of the sensor is what's being protected from the outside environment. And so a lot of your battery rooms are actually considered zone 4 in the ATEX zone 4. And the reason why is because we're keeping hydrogen levels below 1%, and also the distance between the battery system that's producing the hydrogen and the ceiling. And so when you see a catalytic bead sensor in that space, the reason why it's encapsulated is because of the way catalytic beads operate, and not necessarily because the battery room requires explosion-proof equipment. Just a note about that. And then metal oxide sensors created in the 1990s. These basically create there's metal oxide material, and it's like a semiconductor. It's kind of a solid state. They use tin oxide, zinc oxide, or tungsten oxide, and they interact with gases, also creating resistance changes. And so the last one created in 2002 by Sandia Labs in the U.S. It was a solid state precious metal sensor. It can use some of you might know it as palladium sensors, and it uses catalytic properties of a precious metal to detect hydrogen gas. They're fast responding, and they have a very long lifespan. Probably, well, of course, being a precious metal, the lifespan is infinite. They don't wear out. They can become contaminated by the outside environment, such as dust and debris that may be in the site, but the sensor elements themselves typically last a very long time. And of course, when you talk about maintaining these systems, this is what customers typically complain about the most, is what do they have to do to the sensor. And in battery systems, this is where it's important to match the right sensor with the battery system. So let's say you have a valve regulated battery that has a lifespan of 3 to 5 years. That's typically not a problem with any of these technologies, just because these technologies can have a lifespan of, like your metal oxide, your MOS sensor, or your catalytic bead sensor can last 3 to 5 years before you have to start replacing parts. TCD sensors typically last 5 years in most cases, in most of the battery applications. And so that sort of sensor can match that battery type quite well. Where we get into a little bit more complexity is if it has to be calibrated. And like, say, for instance, a catalytic bead system may need to be calibrated every 6 to 12 months. And so if you have to calibrate that, that has to be another maintenance action the customer has to take. Whereas TCDs, a lot of times they'll last the full 5 years without having to be calibrated. And then precious metal sensors, they actually have algorithms inside that they calibrate themselves. They auto calibrate or self calibrate, and they have a system life expectancy of 10 to 15 years. So, which is great for vented batteries or NiCad batteries, because NiCad batteries last that long, and obviously are a lot of sites do not. They don't like to get up into the ceiling and replace sensing systems, except for when they replace the batteries. And so depending on your needs, depending on the lifespan of the battery, and also depending on what kind of maintenance they want to have to do during the time period, will depend on which technology they choose. We also have to watch where we place sensors as well. So in other words, this is a very I should say not application specific slide. So this has with anything that's leaking hydrogen or anything that's creating hydrogen, we have to worry about the hydrogen buoyancy effect. And basically what this just means is that hydrogen is fast moving. It's a very small molecule. And so you want to make sure that the hydrogen system is put within the airstream. So anytime where there's any kind of stagnant air, a lot of times where we're putting hydrogen equipment needs to be within that space. So in other words, hydrogen equipment needs to be where hydrogen may not be able to be evacuated. So if you're putting a hydrogen sensor outside of the airstream, then it may actually miss the evacuate, or how much hydrogen is collecting in that area. So hydrogen will escape very quickly. So if there is a gas purge fan and air is moving, then you're going to want to place your detectors within that stream. Okay, so that's basically the presentation. We have about 15 minutes for questions. I went over a lot of material when it came to the technology of sensing. Basically what a mitigation plan could look like when it comes to detection and notification and what the actual regulations say or the standards say we should do. And then, like I said, regulations when it comes to local authorities, it could vary. We've had authorities who say this is a confined space, therefore we're going to lower the limits in which you need to monitor hydrogen. They say, well, maybe we shouldn't be monitoring at 1%. Maybe we should be monitoring at 0.4%. So a lot of this is based off of the situation on site and how rooms are constructed, and also the technology that's being put in the room. But our authorities who are inspecting our facilities and also permitting our facilities also need educated in the marketplace. And I think obviously that's probably a lot of our goal is to make sure that they're doing what we consider to be what's common sense. It's just enough and not too much. We've had authorities who don't understand the technologies, and so therefore they try to do something that's way too much for the site. And we've also have a lot of authorities who don't pay attention to some of the regulations at all. So but today, with the emergence of this new technologies, documents like the NFPA 855 that are creating a global presence, it's becoming more aware of battery systems, and battery systems that are being deployed for many purposes are being deployed at a very fast rate right now due to AI and other initiatives out in the market. I know we're working on several data centers that are being built, massive data centers, and they're being built by Microsoft and Meta and companies that are really focused on AI. So and authorities are taking notice about what batteries are going into facilities and what the regulations are around that. So do we have any questions?
Yeah, me, I have a question. Sylvia speaking. Good morning.
Good morning.
I work in the bus engineering unit in ADP, and actually it's quite interesting to me to know more about these sensors, and especially I would like to know, honestly, I joined a bit later, so it's also possible that you say that, but I understood that it's quite important that the time response is very quick for this sensor. And I would like to understand better when we check the sensor eventually placed in our container, which should be a good time response time for an hydrogen sensor. And also I would like to understand if there is a kind of optimal location to have these sensors inside the battery container, and if it's, I don't know, like recommendable to have more than one, if one is okay. This kind of to better understand when we do an evaluation inside a container.
Are you talking mainly of lithium batteries in your application?
Yeah, of course.
Okay.
Yeah.
Okay.
Lithium-ion.
Okay.
Yeah.
So in what we've seen in the industry is the code and the standards basically say, of course, we have to prevent accumulation. But in lithium batteries, we've seen OEMs who integrate the containers are also looking at early detection, not just accumulation. So say, for instance, in a lead acid battery, for example, we consider a sensor that can operate in 5 minutes or less to be acceptable, because we're detecting slow rise accumulation. In a lithium battery system, obviously it's very quick, and so what we're seeing in the market is anywhere under 30 seconds. Most of the time it's between 5 and 15 seconds, because they're trying to use it for early detection. Basically tying it into to PLC controls and activating safety systems like deflagration venting or gas purge fans. Now, your question about how many sensors to place in the container, Again, it depends on what your purpose is. If your purpose is to detect accumulation, then if it's in a 30-foot container, we've seen as little as 2 sensors being placed in a container. However, if your goal is to detect a thermal runaway event and gassing from that thermal runaway event, then most of the time we've seen it in every like placing a sensor in every vertical stack of batteries, or every 2 or in between those vertical stacks of batteries, because you're going to need to sense in many more spots than just the ceiling.
Okay, clear. And so I mean, yeah, for a 20-foot container, in case 20 feet generally is the size that we use in order to detect a thermal runaway, like a good position will be like on each rack of the container.
Correct. Yeah, that's what it's going to gas very rapidly. But what we also find is that we have other OEMs who are wanting to know which part of the battery system was gassing first, and so where the incident started to occur. And so to do that, you would definitely have to have sensors throughout each stack of batteries.
But considering the hydrogen, as you said, I mean, it's quite light and it will go upper inside the container. Is it better to place like on the top? If, for example, you put it like in the middle and there is like one model and on the bottom part of the container that is releasing hydrogen. I don't know. Just try to.
Yeah, typically above it, yes, because it is very buoyant. It's going to rise very, very quickly.
Okay, thank you very much.
Yeah. There's different philosophies on that, but what we've seen is we've had manufacturers that put 2 sensors in a ceiling in your application, and they say that there's no point in detecting it in each stack just because it's going to react so quickly and it's going to rise to the top anyway. So it's so they're looking at the whole container. Whereas we have other customers who say, well, we need it at each position so we can see, even if it's seconds of difference, that they want to see which one went off first, second, and third.
Okay, clear.
Okay.
Israel?
Yeah, can you hear me well?
Yes.
Hi, yeah, so great talk, amazing stuff. Thank you very much. I do a lot of gas analysis at the cell level academically. I work at the University of Cambridge and A Coruña, and we do detect a lot of hydrogen, and people get surprised when we show the results. Typically, people don't relate hydrogen as the main gas out. A couple of questions, actually many questions, but I'll just keep it to 2. You presented the data showing a lot of CO2. Was that in LFP cells? Because and how was that analyzed? And second, how do you see this moving to, for example, the automotive section where the packs are a lot more tightly sealed and stuff? And again, great talk. Thank you very much.
That's a good question. Yeah, relating back to. Yeah, if I go back to that slide where, this is the UL 9540A test. So, yeah, in this case, what they were doing is this was a lab environment, of course, basically an NTRL lab, and they had several different sensing devices as they put the battery into thermal runaway. So. In this case, what they were probably using for the hydrogen is they were either using a catalytic bead sensor or they were using a solid state sensor. Those are most popular in these kind of tests because of the ease of calibration. And so now, so as far as the other gases, like I said, they use various sensors. So I'm not exactly sure what how.
Yeah, no, fair enough.
Yeah. Right.
Fair
So
enough.
I'm not sure how they did
use
the others.
we use a mass spectrometer, so it's a little more, targeted to try to find out absolutely everything. And we do see most of it is hydrogen, but it's very, very depending on the chemistry. So
yeah, and I provided sensors into these labs before. That's why I know they kind of use some of our technology as well. But yes, they use mass spectrometry as well as the primary in most of these other gases. Yeah, and so
Brilliant,
what do
thanks.
you, so you said you've seen the same thing, about 30 to 40%?
Yeah, quite likely, but I mean, we try to sort of explore where the gas comes from in terms of inside of the cell, so where it comes from the anode, the cathode, and what kind of
Correct. Yeah.
conditions really enhance this. And I'm working with a team at Warwick, WMG now, trying to explore thermal runaway events, but again at the cell level. So
Okay.
yeah, again, try to pick up the signals quite early on.
Right. Very good. Yeah, I would love to speak with you further and learn more about some of your testing.
Yeah, I'm happy to drop your line later or something.
Perfect.
Si tenéis más preguntas, podéis levantar la mano virtualmente o abrir directamente el micro y preguntar. Nos quedan unos minutos, así que sin problema podemos atender a más preguntas. Okay, so Jeff, I think everything. Oh, okay, we have another question. Maite?
Yeah, sorry. Thank you very much. It was a really interesting presentation. So I'm Maite Paez. I'm working in a company doing inspection and auditions on BESS systems. So we usually have problems for analyzing if the sensor integrating in a BESS container or a BESS module or whatever is a quality one. So yes, I wanted to have some knowledge or about which kind of standard certificate should we ask to the manufacturers for being sure that these sensors are good ones.
Okay, so the certification for the sensor.
Yeah, exactly.
Okay. So one of the certifications we've been being asked for from again, it's a US standard, but it's being asked for on a global level just because it has to do with performance certification. It's a UL 2075. And so obviously you need to meet electrical safety, which is UL 61010 in the US standards, but 2075 is your performance test, and it goes over all the performance of the sensor as well as longevity of performance. And so using as functional safety, we typically recommend, it doesn't have to be UL 2075 if there's another performance standard that you prefer, but we typically recommend a electrical safety as well as another performance certification.
Okay.
And so
Okay, thank you very much.
because the biggest thing you need to know, one of the things you need to know is if the sensor is not performing. And a lot of sensors won't tell you if they're not performing. So one of the requirements of UL 2075 is that the sensor is self-diagnosing. So if anything from the board level is not operating, the sensor will notify or send a maintenance alarm that says that basically a sensor fail alarm that something is not working correctly. Traditionally, the only way that you can tell if a sensor is failing is to expose it to hydrogen and do a calibration or a bump test. And so so new technologies now in sensing, they actually have self-diagnosing properties, and so you can the sensor will notify you if it's not working properly. That's very important in functional safety.
Okay. Thank you very much.
You're welcome.
Okay, so next question. Begum?
Hello. Thank you for the talk. Sorry, I missed some part of it. But So I'm currently working with the online gas analysis in the single cell level. I think Israel mentioned I'm from the University of Warwick. We're working together. So can you please let us know, like, how did you measure the total vent gas volume in the large level, like a pack level?
Yeah, so I haven't I don't really do a lot at the pack level. And I know there's various methods like spectrometry to be able to tell what gases are in the pack level. You know, that's something I've been covering more of the site safety in this presentation, but I do know that there's a couple of you here from the university level that do that from the pack level, but yes, that's, you know, so basically, you know, we've seen various methods, and if you want to send me an email, I can certainly send you, you know, some folks to talk to about how they do that at the pack level.
Okay, thank you.
No problem.
We have a question on the chat. Pedro, do you recommend the gas detector to be specific to H2?
That's a great question. We do, yes. A lot of general gas sensors will pick up various gases that could be in the atmosphere, like we said, with the cross sensitivities that could exist within a site. So an H2 specific sensor is important to be able to distinguish, you know, between what, you know, various things that could be on site. In fact, like I said, with cross sensitivities to CO and to any other gases that could be present. In fact, a lot of the solid state sensors, like you know, one of our sensor technology, for example, is hydrogen specific, and there is a physical barrier that no other molecules can get through the physical barrier. Since hydrogen is so small, helium might be able to get through because it's small as well, but everything else is blocked because of it can't enter the substrate. And so as other systems are doing it algorithmically with firmware to be able to make it hydrogen specific with conditioning. So, but yes, we do recommend that it's not just a general sensor is used. It's used it's definitely used with a hydrogen specific sensor.
Thank you, Jeff, and thank you, Pedro, for your question. Do we have any more questions before ending the webinar? All right, so I think that is it. Thank you, Jeff, for your presentation. I remind you that the recording of the webinar and the presentation itself will be available on our website. So if you have any question or need more information about the H2 scan, you can contact Jeff and the email address you can see in the presentation. So thank you all for attending the webinar, and I'll see you next time. Next webinar we're gonna organize from the platform.
Thank you.
Thank you very much. Very, very interesting.